All right, I'm going to be going over section 33. This is the first section on machine learning from Mod 5. And this is K nearest neighbor, which is one of the, so we've gone over a couple of machine learning algorithms, linear regression, which is used for regression models. And there's actually a pretty good little flowchart that sklearn has. Yeah, this thing, choosing the right estimator. K nearest neighbor is right here. So this is a nice little flowchart on helping you decide which algorithm to use. What we've gone over is we've gone over lasso regression, we've gone over ridge regression. So if you have less than 50 samples, then you need to get more data. Are you predicting a category? If you're not predicting a category, no. Are you predicting a quantity? If the answer is yes. If you have less than 100,000 samples, then few features should be important. Then you use lasso regression. If that's not the case, you can use ridge regression. So that's a nice little flowchart. What I like about this is if you click on it, you can go to the documentation for that particular function or algorithm, I should say. And then we've also learned logistic regression, which they don't have every single algorithm on this sheet, but now we're going to be learning about K nearest neighbors classifier. And we've also learned naive Bayes. So K nearest neighbor, like I said, I would say like decently popular algorithm. It's nice thing about it is it's really easy to understand. Yeah, and I forgot to open this PDF, so bear with me 1 second. Study group. All right, so in this sheet, so in the first ring, the center, you write your name, then 3 people closest to you who you take, for whose advice you take, 5 people a little less close to you, and then 7 people, etc. So I'm just gonna annotate this thing. Annotate. So you write your name in the middle. And I'm just gonna do first initial for all this. Then 3 people closest to you. And then 5 people in the second ring. These are just initials. And then 7 people after that. I don't know why I wrote it down. Yeah. 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. One more. Okay, so finally did that. So now if we go to this Hangout, and I'm going to keep that. So if for each of these friends, I'm going to go back to this worksheet, would they choose seeing pets, or would they choose seeing Rocket Man? So open this back up. So I'm going to circle the people that would see Rocket Man. Or I'm going to circle Rocket Man with orange. And that is orange. So they would see Rocket Man. And this is just some assumptions versus pets. All right, cool. So So if I pulled the inner ring of people, which movie would they see? Um, so if I just pulled the inner ring of people, um, I would end up seeing Rocket Man because 2 is greater than 1. One person does not want to see it, the other 2 would. Or this person would prefer to see pets. So now if I pulled the first and the second ring, so the first and the second ring, there are a total of 8 people. 4 of them would see Rocket Man. 4 of them would not. So then we go down to a tie, and this is a great example of one of the downsides of k-nearest neighbors is usually if you have 2 classes, you want to pull an odd number of people so you don't have a tie. So there's some ways around this. You could start ranking these people, like how close they are to you. So you have these 3 people, are these 2 people closer to you than this person, or is there these people closer to you than these 3 people? If that's not the case, then you could rank them based off not just like in categories, but like overall closeness. Some different approaches to that. And then if I do everything, so there's a total of 15 people, 1, 2, 3, 4, 5, 6, 7, 8. 8 people would and 7 people would not. So in this case, more people would vote for to see Rocket Man than would not see Rocket Man. So this is kind of an idea how k-nearest neighbor works. And I'm gonna clear all this off now. Okay. Yep. So overall, I ended up seeing Rocket Man. So the idea behind this is that if you're trying to predict something, if in a feature space, the points closest to it are a particular category, the assumption is that they are the same category. So like the idea is that you're like close, like when people are looking at like demographic type information, if they know that your neighbor has certain policies, or a lot of times they can make the assumption that the neighbors of their neighbor, the next door neighbor, has the same kind of views and stuff. And we're doing this instead with like voting and stuff like that, but instead we're doing it with like data. So if we know that for the Titanic data set, we know that people that, if we remember the movie, young people survived at a higher rate, and then children, not children, but people that paid a lot, rich people in first class. So if we have a person that we're not sure if they survived the Titanic and they are 5 years old and they were in first class, we'd look at other people that were also 5 years old and in first class and make the assumption that, okay, 4 of them survived and 2 did not. So we, based off that, we would make the assumption that they did survive, or make a guess that they would survive based off that. And you could also do like a probability. So there were 6 people that were 5 in first class, 4 survived. So there's a 66% chance 4 divided by 6, and a 2 divided by 6, or 33% chance that they did not survive. So we're going to be revisiting the Native American diabetes data set. So we're trying to predict whether people have had diabetes or not. I believe we have gone over this data set at least a couple times. It's kind of a famous data set from this UCI machine learning repository is pretty famous, and they got some pretty famous data set that people use for machine learning, like the IRIS data set, the WINE data set, but there's also some other stuff in the Native American diabetes data set is pretty popular. So the objective here is to be able to implement the k-nearest neighbor classification model and utilize a visualization to identify the best value of k. So the k nearest neighbor, it works by, let me open a whiteboard. Where did my marker go? I was hoping to change colors. There it is. My Zoom window's in the way. There it is. So if I have a red point here, 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 and then I also have some blue points that are right here. If I have a black point that is right here, and I don't know if it's a red or if it's a blue, and I wanted to look at, and I'm going to use the nearest neighbor algorithm. I wanted to look at the one nearest neighbor, k equals 1. I would look at what data point is closest to it. In this case, it's this blue point right here. So I would make the assumption that this is that this blue point, that this black point, I should say, is blue. But if I wanted to look at the 5 nearest neighbors, I'd look at the distance between them. So 1, 2, 3, 4, and 5. And all 5 of them are blue. So I would make the assumption that this black point is blue. So let me change the location of it. So what if it was right here? So right in between them. If I wanted to look at the nearest neighbor, this is, I'm just eyeballing this. So I would say this is the nearest neighbor. I think it's a little bit closer than that one. If I wanted to look at the 1 nearest neighbor, I would probably say it's a red point. But if I wanted to look at the 2 nearest or the 3 nearest neighbors, it'd probably be red, red, and then blue. So it would be still be predicting red. But if I did like the 5, it'd be 1, 2, 3, 4, 5. So now it's blue. So that's kind of the idea of k. You have to decide what is the best value of k. And we will show you how to do that. So what is the k nearest neighbor classification model? Kind of gone over that. How to use scikit-learn's grid search function. So k nearest neighbor is known as a lazy learner. So learning methods simply store the training examples and postpone the generalization building a model until a new instance must be classified or a prediction made. So what that means, a lazy learner, you will hear that a lot about k nearest neighbor, that it's a lazy algorithm. So with linear regression, to make a prediction, you have to come up with a slope and an intercept. Going back to, now if we have a data point, that's not the best fit line, but you get the idea. I can't draw. You need to know what the slope is and the y-intercept at this point. So y equals mx plus b. We need to learn what that is. With logistic regression, we need to know what that sigmoid function is. What is that sigmoid function that's going to fit this data? With k nearest neighbors, you don't have to learn anything. All it does is it waits till I get a data point and then looks at whatever you specify for k. So whether that's 1 or 3 or 5, and then just calculates it. So and how that impacts you is with those other algorithms, fitting takes a while, but predictions do not take very long because you already know what the slope and intercept is. With k nearest neighbors, the fitting, you're not doing anything in the fitting. So that does not take very long, but the predictions can take a little bit longer. So if you're trying to do a prediction in real time, sometimes k nearest neighbor, if you have, so this is just the 2 dimensions, x and y, but imagine if you had 50 dimensions and you had to calculate the distance between points in 50 dimensions. That can take a while. And if your k is a large number, it can take a while. So keeping that in mind is really important. And then k-nearest neighbor is a non-parametric model where linear regression, logistic regression, they both assume there's a distribution there. This can handle any sort of distribution. And so kind of went over this, so I apologize. What should the gray point be? So the gray point is right there. Should it be purple or should it be this teal color? So there's some steps to it. First, you select the k value. Should it be 3? Should it be 5? We'll show you how to decide that. So let's say we select k to be 3. And our 1, 2, 3, 4, 5. Yeah, k equals 3. So we have the 3 nearest points. 2 of them are purple. 1 of them is teal. So the prediction is that it is a teal, not a teal color, a purple color. So when doing a binary classification, there's some ways to handle if you have a tie. If you do binary, you select a odd number, so there can't be a ties. But if there's a multiple classes, and you have a tie. So what if it is, there's 3 classes, and you got 2, 2, and 1 is the count, and you did k equals 5. You could reduce the k by 1 to see who wins, or you could weight the votes based on the distance of the neighbors. So this is a multi-class problem, and each color represents a different class. So if k equals 1, this is the decision boundary. So how to read this is, I'm gonna make this a little bit bigger, sorry. Is if there was a data point, a random data point, I'm gonna annotate again. So if I have a black data point right here, and k equals 1, the prediction would be green. Right here, it would be green. Right here, it would be red. Right here, it would be red because the closest data point is red. Right here, it would be blue because the closest data point is blue. It's farther away than red. So how to read it in the shaded area is this is where the decision boundaries are. Yeah, I'm gonna clear this. Now, if k equals 5, here's what the decision boundaries are. And what you will see when you increase the k, these decision boundaries are going to smooth out a little bit. So like here, we have little tiny decision boundaries. But right here, it would be all green because k equals 5. And of all the 5 closest points right here, it's no longer going to be a red. It's going to be green. So essentially what's going on is you're adding a little bit more bias, but you're also getting a little bit more improved variance. Like when k equals a really small number, it can sometimes overfit. Like this area probably should be green, just looking at it. It's green all the way around. This might just be an outlier point. Or this point might also be a green because blues looks like they're right here mostly, and you know. So how do we calculate the distance between points? So right now, up to this point, we've just been kind of eyeballing it. So we put a point right here. There's this distance is really small. This distance is really small. This distance is really small. This distance is a little bit larger. This distance is a little bit larger. So there's a mathematical way to do this, Euclidean distance. This refers to the distance between 2 points. These points can be in different dimensional space and are represented by different forms of coordinates. In a one-dimensional space, the points are just on a straight number line. So in a 2-dimensional space, calculating Euclidean distance, it's x1 minus x2 squared plus y1 minus y2 squared, and then you take the square root of it. In a 3D space, it's just the same idea, x minus x squared plus y minus y squared plus z minus z squared, and you take the square root of it. And this can obviously scale up to however many dimensions that you have. So we're going to now implement the KNN classifier with sklearn. So I'm going to load in this data set and take a look at it. And what I'm trying to predict here is I want to predict what the outcome is, whether they have diabetes or whether they do not have diabetes. And I'm just looking at my data set here. And I want to grab a column. Oh man, diabetes. So there are 500 people in this data set that do not have diabetes, 268 that do. Let's make a bar plot. Doesn't look in matplotlib is imported, so import matplotlib pyplot as plt. And for some styling, so good portion, almost double amount of people that do not have diabetes in this data set. When you're using scikit-learn, you need to make an X and a Y. So my X is, my Y is my outcome. My X is everything that I'm going to use to predict the outcome. And I didn't run this cell. So something, oh, we haven't got to it yet. So when I've used this, I want to train it on my training data and then test it on my testing data set to make sure to validate my results. So scaling, really important for this. When we think about this, if something is in the scale of thousands and then something is in the scale of decimals, because of this algorithm, it would weigh the thing that's in the thousands so much more important than the thing that's in the decimal. Because this is a distance metric, you want everything in the same scale. In this article, they talk about the difference between standard scaler and min-max scaler. So z-score standardization, which is putting it in a z-score, and then min-max scaling. So which one is better? This person, Sebastian Rashka, probably mispronouncing that. He's kind of a famous data scientist on Twitter. I think he's a professor at the University of Wisconsin. So in clustering algorithm, standardization may be especially crucial in order to compare similarities between features. Another prominent example is the PCA, which we'll cover later, which we prefer standardization over min-max scaling. So yeah, he doesn't really give an answer. So in neural networks, a lot of times they require data to be on a 0 to 1 scale. So that's an obvious example when to use a min-max scaling. I will typically use z-score standardization on a problem like this, but I would imagine you get the same result. So yeah, standard scaler and then min-max scaler. So we are using standard scaler here, which is that z-score standardization. We're going to fit the data. If you remember, k-nearest neighbor is a lazy algorithm, so this fit is not going to do anything, but the underlying structure of scikit-learn, we still have to do it. And I misspoke. I'm not using k-nearest neighbors. So I need to, this is just for scaling. So I'm fitting the z-score standardization on my training data, then I'm going to transform my train and my test data set. So run that. So scikit-learn's 4-step modeling pattern. Step 1, import the class that you plan to use. class I plan to use is this k-nearest neighbors, so I'm importing it. Next, I need to instantiate the estimator, which is this. So in this first time, I'm going to use the in neighbors, which is my k value, to be 1. So I'm going to look at the 1 nearest point. Fit the model with the data. You always have to do this, even though, this is kind of the point I was trying to make earlier, even though that the k-nearest neighbors is a lazy algorithm and nothing is happening in the fit stage, we still have to do it. That's just part of scikit-learn. So going down here, well, that's not what I want to do. If we print it out, and I messed it up. I could have sworn it said n equals 1. Let me run that again. I'm pretty sure we're going to use n neighbors equals 1. Equals 1. So now if I print this out, n neighbors is 1. Next, we need to fit the data. So I need to fit it on my training data set, so X train and Y train. And then predict the response for a new observation. knn.fit, which we've already done. Then I want to predict. And then I'm going to predict how well I do. So I get about 70% accuracy and about a F1 score, which is the harmonic mean of precision and recall of 54%. The reason I like F1 score can be good is we remember we have an unbalanced data set. So value counts. And diabetes. Yeah, I cannot spell. So if we predicted everything to be a class 0, we would get 65% accuracy. So we got 70% accuracy, which is about a 5% boost from the kind of the baseline accuracy. So this accuracy shows 70%, but it's only a 5% boost from just randomly guessing everything to be a 0. So it's honestly not that great. So whenever you look at accuracy, you kind of have to look into the context of how balanced or unbalanced your data set is. And F1 score kind of captures that a little bit more closely. You'll see on a lot of Kaggle competitions, they'll never do accuracy because of this reason. So we're going to plot a confusion matrix. And this is just some code. This is code taken right from scikit-learn. And this makes a really not so great confusion matrix. I like this library called Yellowbrick. I'm going to show that real quick. Yellowbrick. For confusion matrices, I think they usually make a pretty good one. This is a library that works right on top of scikit-learn. So confusion matrix. So let's grab all this code. Whenever I'm like trying something out, I always like just starting out with some baseline code. So my classes are 0 and 1. And my model, what did I name my k nearest neighbors? So I named it k and n. So let's do k and n right there. And I need to import the library. So Yellowbrick. used this library not too long ago and it worked. Oh man. So I don't think this is gonna work. NumPy array has no object fit to create the confusion. Oh, this needs to be CM. There it is. So this shows my 69% accuracy, which is, yeah, the same accuracy there, but now we see like how well we did. I've always liked these ones a little bit better just because they do all the kind of, what is all this garbage here? So this is my actual, I believe, yeah, my true class and your predicted class. We can add labels. Plot.label. Actual. Y label. Plot.x label. Predicted. And it's a little hard to read, so let's make the font size a little bigger. Take the time to make your labels kind of readable. It is worth it. And like we can do it for our text too, xtext. So our xtext are a little bit bigger. Plot.ytext. So there were 99 instances where we got it correct, where we predicted 0 and it was 0. There was 34 instances where it was a 1 and we predicted it as 0. 24 instances where it was a 0 and we predicted it to be a 1. And then 35 instances where we got it correct and it was a 1 and we predicted it to be a 1. So that was using KNN equals 1. So remember, we got an F1 score of about 0.55. So let's see what we do when we get K equals 5. So our F1 score improves pretty significantly. So I'm gonna run that again. K equals 5. So now we're up to 108 and 44. So these numbers are getting bigger. We saw that this and this. You want these darker colors. So this is kind of a lighter yellow. These are about equal, 34 and 35. Now we're starting to see it. This is a little bit darker than that. So that's a good sign. And then we can also look at the classification report. So we have our precision and recall for each of our classes. And then there's a confusion matrix again. Again, I like using yellow brick a little bit better. So now we're going to search for an optimal value of K. We're going to look at different K values. We're going to choose 3 of them. And we'll plot it out. And we see that for a K value of 3, we get a F1 score of almost 72. Be curious if we got, let's do it up to 10. We see that once we go up to 5, it kind of just, it kind of converges in a way where I would probably choose 5 if I was doing this. So, yeah. So I kind of already touched on this. K size does impact. So when you have a small K value, you're prone to overfitting, so low bias and high variance. When you have a large K value, you're prone to underfitting. So high bias, low variance. We kind of saw that with this. When we have a K value of 1, we see these little tiny pockets because they could be in a single outlier point that can end up making an impact. But when you make K a little bit larger, it smooths it out. There's some resources here. This Introduction to Statistical Learning. This is a pretty famous book. And they also wrote some, had some YouTube videos, but they have a nice YouTube video on K-nearest neighbors. They teach everything in R, but everything, the overall concepts are obviously transferable, and R could be something you might want to learn later on. And then this is a YouTube video that I like. I'm a big fan of this Josh Starmer guy. I think he's really good at explaining things. So here's another video that'd be worth checking out. Yeah, I got, I think I have a data set in here. I want to kind of play around with in the remaining time. Something else that you can do with the K-nearest neighbor is, I follow sports a little bit, so you could also use it to find the player that's most similar to someone based off the same idea. So I already imported pandas, so let's do df equals pd read CSV, NBA CSV. So this is a data set of NBA players. If you're not familiar, NBA is a basketball league here in the United States, and we just have some different players. We have 54 columns. I just want to look at 3 columns. 3 kind of metrics that are commonly used in the NBA is points, rebounds, and assists. So I want to just start with looking at a single player, and the player I want to look at is LeBron James. If you're not familiar with him, he's one of, if not the best player in the league right now. He's getting a little bit older, but I believe this data is from 2017, so it'll probably reflect that. Total rebounds, which is TRB, which is total rebounds, and assists. And name is singular. And oh, I forgot the capital L. So in this season, LeBron had 1,954 points, 640 assists, and 646 assists and 640 rebounds. So which player had the closest season to LeBron? I'm going to use a little subset, a little cousin of K-nearest neighbors called nearest neighbors. Neighbors. Import nearest neighbors. So first I'm going to import it, then I make an instance of it. Then I fit it. Points, total rebounds, and then assists. So I'm going to be looking at the 5 nearest neighbors to LeBron. So, and LeBron is number 293. Total rebounds and assists. And I got an error. And this is kind of common with scikit-learn. It does not like taking a single instance like this. So I'm going to have to use this dot reshape like it specifies. Dot values. Dot reshape. 1 and -1. All right, so it gives you the distance, and then it gives you the index of each of these players. So you'll see that the first person has a distance of 0 because that is LeBron James. But we'll take a look at the other ones. 293, 160, 425, 217, 88. And then player name. So we see the most similar players to LeBron James are LeBron James, I never know how to pronounce this guy. His nickname's the Greek Freak. Stephon Curry, Jimmy Butler, and Damian Lillard. You may remember I didn't scale the variables, so it's taking into account points as the most important. So if I wanted to scale the features, I'm going to do this really quick. I want to steal it, just going to steal the code. So let's see how much things change by using scaled features if the players change. Now I'm going to do fit transform. And then in fit. And then I want to put in my LeBron James. I need to transform this data. And I need to reshape it. I got another call. I have to jump on here in a second, so I'm kind of trying to rush a little bit. Sorry. All right. So in nearest k neighbors. And let's go back to df.look. $293, $160, $425. So ends up with being the same players, even if I didn't scale. In this instance, it works, but it's not always going to work. So you should scale your features. So it looks like the Greek Freak, Stephon Curry, Jimmy Butler, and Damian Lillard are the players most similar to LeBron in 2017, just based off points, rebounds, and assists. So hopefully that was useful. If you have any questions about this, do let me know. Thank you.